Hello everyone, in this video we're going to discuss the longest string chain problem. In this problem we are given a list of words and we need to find the length of the longest string chain that can be formed using any combination of the given words. A string chain is defined as any chain of words where you can insert a single letter into a word to form the next word in the chain. So for example, if we're given these 5 words as input, then one possible valid chain we can form is IH to LIH to LIGH to LIGHT. You can see how for every word in our chain, we add a single letter to form the next word in the chain. Since this chain is actually the longest chain we can form, if we were passed this as the input, we would return 4, which is the length of our chain. Some constraints and clarifications for this problem are: the first is that a chain can be one word long. This is just a single word. Every word in the word list is going to consist of lowercase English characters. And finally, every word in the words list is going to be limited in size to some constants. Let's just say that constant is 20 for the sake of this problem. Each word will also be at least one character long. Now that you hopefully have a better understanding of the problem, let's look at the first possible solution. For our first solution, we are going to use a graph to solve the problem. The first part of the solution is creating a directed graph where each vertex represents a word. An edge or connection from word A to word B means that you can add one letter to word A to form word B. So for example, if we're given this as our input list, then the graph that we are aiming to construct should look something like this. You might want to pause the video here and check for yourself how for each connection in the graph, you can only get from one word to another if and only if you can add one letter to the first word to make the second word. Now if we constructed this graph correctly, the next step is to traverse the graph and find the longest path. This is a pretty straightforward problem which you can solve with either a breadth first or depth first graph traversal. So for this particular graph here, we would find that the path I've colored in blue is the longest path, and that path's length is 4, which is our correct answer. So basically I've broken down this solution into 2 major steps: constructing our word graph and using that graph to determine the longest string chain. Let's take a look at the implementation for constructing a graph. First, we can define a separate function which is going to take in the words parameter. In this function, we create a graph variable which is going to be a map from a word to a list of words. The list of words represents the other words that a word has a connection to. This is a adjacency list representation of a graph. Ultimately, this is what we're going to be returning. For every word, and for every letter in this word, we're going to delete that letter, forming a potential candidate for a predecessor node to this word. Now, if this potential predecessor is also in the word list, we know that there should be a connection from the predecessor word to this word we are currently iterating on. We establish this connection by getting the predecessor's adjacency list in the graph and appending the current word to it. In order to check if the predecessor is in the words list, I've made a word set and used that instead. We're using a set as opposed to a list to speed up the time complexity of that if statement check. That's it for constructing the graph. So now let's move on to traversing the graph that we have created. Like I mentioned earlier, this can be done with BFS or DFS. I'll just demonstrate the DFS way in this video. Our first step is to initialize 2 dictionaries. One will keep track of which vertices we have visited, and the other will keep track of the longest distance that can be achieved from this vertex. For every vertex in the graph, if the vertex has not been visited yet, we're going to call a DFS helper method to traverse the graph. In our DFS helper, we mark this vertex as visited, and then we loop through the neighbors of this vertex. Remember that the neighbors is the adjacency list of the other vertices / words that we can reach from this vertex. For each of these neighbors, we need to determine the distance of the max string chain from this vertex, so that we can say, okay, whatever that number is for the neighbor, let's add 1 to it, representing us adding this word / vertex to whatever the neighbor chain has. We can determine the neighbor's distance by making a recursive call to the DFS helper if the neighbor has not yet been visited. If the neighbor has already been visited, then we know that the distance has already been determined, so we can just get that from the distances map. This is what we do in our next step by assigning the value in the distances dictionary for the neighbor to a variable called neighbor distance. Once we determine what the neighboring distance is, we see if that neighbor distance plus 1, the plus 1 is accounting for us using this vertex itself in the chain. We see if the neighbor plus 1 is greater than the current length in our distances dictionary for this word, and we assign the max of the two for the distance for this vertex. That completes the implementation of the helper method. Back to our main DFS traversal. Once we have finished iterating through all the vertices, we can now run a for loop through all the vertices to figure out what that max chain distance is and return that distance. And that takes us back to our original function call, where we ultimately return longest. Okay, now that we have gone through this solution, let's analyze the time and space complexity. In order to do that, we need to define some variables. First, I'm going to define n as the length of words input that we are passed in. Second, I'm going to define a as the length of the longest word in the words array. Remember, in our constraints, we said that the largest this could be is 20. So really, for all intents and purposes, this is a constant number. But I just want to define it as a variable here because your interviewer might change the problem a bit and say that there is no upper limit to the word length. So the first two costly things is our double for loop when constructing our graph. This is going to be O of n times a. Within the for loop though, we also slice a string view of the predecessor, and we check if the predecessor is in the word set. Both of these operations are O of a, but since they happen sequentially in the loop, this means the work of the inner loop is a plus a. So that leaves us with n times a plus a as our work for constructing the graph. Now for the DFS of the graph, you might already know that DFS is going to cost us vertices plus edges, but let's see where that happens in our algorithm. The vertices part comes in here, where we make sure to visit each vertex, and also here, where we mark off every visited vertex so that we don't revisit already visited vertices. The edges part of the complexity comes from us visiting all the edges or neighbors here. Unfortunately, the maximum possible edges is n squared if you think of a densely connected graph. So to simplify this down, we can kind of get rid of the a's because in this video I've said they are all going to be below 20. But again, keep in mind your interviewer might not say this, but for this video, since it's constant, it means we can drop them. And here we can see the dominating term is n squared, so that is our overall time complexity. Now onto space. The major extra space we are using is in the construction of our graph. The graph has vertices and edges, so the space complexity is going to be O of v plus e. V is going to be n, and like we discussed earlier, e is going to be n squared, so our space complexity is n squared. So now that we've discussed time and space, that ends the discussion for our first solution. Let's try and improve it with a second solution. This solution is very similar in concept to the first solution, but instead of a graph, we are going to do some dynamic programming. In our previous solution, we constructed a graph where for any word, if there was a word connected to it, it meant that we could form a chain between the previous word and this word. For our dynamic programming solution, for any given word, we are going to determine the max chain by looking at all the possible words that could be connected to this word. Then, we're going to see what their max chain is, and then add 1 to it. So for example, if the word of interest is this 5-letter word here, there are 5 possible 4-letter words that could form a chain with this one. Just like in the last solution, we'll call these predecessors. Of these 5 possible ones, let's say that 3 of them are actually present in the word's input. Let's pretend it's the first, second, and fourth ones. So assuming we did dynamic programming correctly for each of these predecessors, then we should know the max chains that can be formed using them. So our DP map would have some terms including the ones for these predecessors. The DP map is a map where the key is a word and the value is the max possible chain we can form with that word. So ultimately, in trying to determine DP of light, we take the max of the DP values of the predecessors and add 1 to it. The +1 is for adding this particular word, light, to the chain. So in this particular case, DP of light would be 5. Some more things I'd like to point out are that this solution relies on the fact that for every given word in our input, we have computed all the DP values of this word length minus 1. So if we are trying to determine the DP value of a 10-letter word, we need to have already computed all the DP values for 9-letter long words. This is going to require us to compute the DP values in increasing word length, so we're going to need to sort the words by length. Okay, let's start writing the code and trace through a detailed example while doing so. The first step is to sort the words by length so that we can compute their DP values in increasing order. And actually, you might have realized we don't have to do a full-blown sort to accomplish this. What we can do is instead just bucket the words by their lengths, and then iterate over each of the buckets in increasing order. This will save us some time complexity, and you see that later when I analyze the time and space of this solution. So let's do that here with these first two separate functions I created. The first is called determine longest word. All it does is it iterates through all the words in the input array and returns the length of the longest word. So if this here is our input of words, the function would return 3 because the string with the longest length is ABC, which is 3 letters long. For the next step, we need to build the length buckets. This function is going to return a map where the keys are word lengths and the values are a list of words with that length. This is first done by constructing a map with keys from 1 to the length of the longest word. Then for each word, we find the right bucket and append the word to it. Our next step is to initialize our DP table. So as a refresher, remember that DP of word is going to represent the longest possible chain we can construct ending in this word. So to start off, before our computation, we can set them all to 1, because the word itself represents a 1-word long chain. We are also going to use a word set so that we can more quickly determine if a word has the input array or not. We will use this set in a bit. Now this is the DP part of the algorithm. For each length in the length bucket from 1 to the longest word, and for each word in that bucket, and for each letter in a word in a bucket, we are going to construct a possible predecessor by slicing this jth letter out of the word. If this predecessor has been given to us in the word's input, then we set the DP for this word to be the max of the DP of the predecessor plus 1. This is essentially adding this word to the maximum chain of the predecessor and comparing the length of this chain to the current longest chain for this word. Let's run through this portion of the code with our example on the right. So I starts off as 1, which means length of buckets of I is going to be the list with just A in it. So A is going to be our word. J starts off as 0. So this means that predecessors is the empty string. The empty string is not in the word set, so we skip the if statement and move on to the next iteration. The next iteration actually goes to the I equals 2 iteration of the I for loop. This means that length buckets of I is equal to the list of BC and AB. So word is going to be BC in the first iteration, where J starts off as 0. This means that the predecessor is going to splice out the first position, which is B, so predecessor is just C. C is not in the word set, so we don't enter the if statement. On our next iteration of the J loop, J is 1, which means predecessor is B. The predecessor is not in the word set, so we skip out of the if statement and move on to the next iteration. In the next iteration, the word for the for loop is now AB. J starts off as 0, and that means predecessor splices off the first character, leaving us with just B. B is not in our word set, so we can move on to the next iteration, where J is 1, which means that predecessor is A. And finally, for the first time, our if statement passes because the predecessor, A, is in the word set. So we set dp of word, which is AB, to the max of either the dp of predecessor plus 1, which is 1 plus 1, which is 2, or the current dp word, which is 1. The max between 2 and 1 is 2, so dp of word is now 2. On a conceptual level, this operation represents us accounting for the A to AB word chain. This word chain of A to AB is 2 words long, and it is the longest chain that we can form which ends with the word AB. We now move on to the next iteration, which bumps us back up to the I for loop, which is now 3. So length buckets of I is the list with just ABC in it, which means word for the first iteration is ABC. So when J is 0, we are splicing out the A in our word, so our predecessor is BC. BC is in our word set, so the if statement passes and we enter the if statement body. Here we take the max of dp predecessor, which is BC, which is 1, and we add 1 to it, so that's 2. And we compare that to dp of word, which is 1. The greater of 2 and 1 is 2, so dp of word becomes 2. Conceptually, this represents us accounting for the word chain of BC to ABC, which is 2 words long. Now we move on to the next iteration of the J loop, which is J equals 1. So our predecessor here is AC. AC is not in our word set, so we skip the if body and move on to the J equals 2 iteration of our J loop. Here, predecessor is AB. This is in our word set, so we enter our if statement body where we compare dp of predecessor plus 1, which is 3, and dp of word, which is 2. The greater of 3 or 2 is 3, so dp of word becomes 3. Again, conceptually, this is us comparing the word chain of 2 from before, BC to ABC, to this longer 3-word chain of A to AB to ABC. Obviously, the 3-word chain is longer, which is why it replaces the 2 as the new dp value. Once that is done, we finish this iteration, and that was actually the last iteration, so we just jump down and return the max of all the dp values. This is the maximum chain we can form, and for this example, it's 3. Okay, that is it for the tracing. The final thing to do is analyze the time and space complexity of this solution. We're again going to be using these 2 values in our analysis. N is the amount of words in our input, and A is the max length of any word. So the first thing we do is the call to determining the longest word. This is going to be an O of N operation because we iterate through all the words. Next comes building the length buckets. This is an O of N operation as well because we just iterate through all the words. I should note that in some other languages, this might be N times A if a copy of the string is being made when it's appended. But I believe in Python, only a copy of the reference is made. So the append is an O of 1 operation as opposed to an O of A operation. It is also at this point you can see the advantage of using the bucket mechanism as opposed to a full-blown sort. A full-blown sort would have costed us n log n, and that would have been unnecessary. Now for the time complexity of the dynamic programming portion of the algorithm. We have these 2 outer for loops. The combined iteration of these 2 loops is O of n. This is a bit deceptive, but if you think of when these loops run over the course of the whole algorithm, it runs once and only once for each word, so that's O of n. For the J inner for loop, worst case this runs max of length of a single word, which is A. And for each of the J for loops, we do A plus A work. One A is for the slice operation, and the other A is for checking if the predecessor is in the word set. All this simplifies down to O of n plus n times A squared. All that simplifies to O of n because in this video, we are treating a as a constant less than or equal to 20. Again, your interviewer might not make this constraint, in which case you would have to account for a in your time complexity, and you couldn't just drop it like we do here. For space, the major data structures are our bucket structure, which is O of n in Python, but maybe O of n times a in other languages. There's also the word set, which is O of n times a, and also the DP map, which is n times a. So worst case, our space complexity is O of n times a. Once again, we drop the a term. When we drop the a term, this simplifies to O of n. Okay, that is it for the second solution. This was a long video, but to recap, we went over two solutions, a graph solution, where we built a predecessor graph and did DFS on it. That solution was slightly slower than our second solution here, which uses dynamic programming. I hope you found this video useful. As always, thank you for watching and good luck on all your interviews.